I am Anil Kumar. Welcome to my series on trigonometry. Now we are discussing how do we graph trigonometric functions, how do we find the characteristics, and how do we find equation from the graph. In this video, we will learn about the tangent function. We'll discuss the topics like characteristics of tangent functions, transformation and image point mapping, graph of transformed tangent functions. To write equation from the given graph, we'll be working both in degrees and radians and share with you examples which we have seen in test papers. Graph of some tangent functions are given to you here. Let us take up the characteristics to begin with. So let's talk about the properties of tangent function y equals to tan x. Domain is set of real numbers except the odd multiple of 90 degrees or pi by 2, right? As you know, you can write tan x as a ratio of sine x over cosine x, correct? So clearly, cos x should not be equal to 0. The points where cos x is 0, those will result into vertical asymptotes, and these are shown here on the graph as the vertical lines, dotted lines. So clearly, the domain will not include pi by 2 and its odd multiples or 90 degrees and its odd multiples. As far as range is concerned, all real numbers can be the value for the tangent function. As you can see and as you know, the tangent function is always increasing. It has no turning points. There are no local maximum or minimum. And that is one reason why the strategy to sketch tangent function and cotangent function is different from the strategy which will be working for the sinusoidal functions, sine, cosine, secant and cosecant. Perfect. So when you look into my videos on how do we sketch graph of trigonometric functions, the focus is very clear. We deal with tangent and cotangent in one manner and in very different way for the sinusoidal functions sine, cosine and their reciprocals. Now, tangent and cotangent function both have vertical asymptotes and they kind of give you the boundary within which we can get the principal or the main characteristic or graph of the function, which can be repeated to get the complete graph, right? Now, just as sine function, tangent function has odd symmetry. It is symmetric about the origin. When I say odd symmetry, it means what? It really means that tangent of minus x should be equal to minus tan x, correct? That is what is meant by odd symmetry. Now, the period of tangent function is pi or 180 degrees. The x-intercepts are where the sine values are 0, right? Those are the x-intercepts, and these are at multiples of 180 degrees or n pi. The y-intercept is at the origin. Perfect. Now, here is students' activity. You need to explain why the graph of tangent function approaches positive infinity while approaching from left side of 90 degrees and negative infinity while approaching from the right side of 90 degrees, right? So what we're trying to say here is, if you look at the graph of tangent function, you can clearly see that while approaching 90 degrees from the left side, it approaches positive infinity, and on the right side, it approaches negative infinity. What is the reason for that? Okay, so that is your exercise. Let's move forward and understand some principal values for the tangent function. Now, the principal cycle of tangent function, which is y equals to tan x, is between minus 90 and plus 90. Now, it is important to understand that the tangent function has period of 180. So we can actually graph a cycle in any interval of 180 degrees, right? And we can repeat it over and over again to get the complete graph on the required domain. Perfect. Now it is also important to understand that the tangent function has odd symmetry and the odd multiples of 90 are actually vertical asymptotes, right? So we have vertical asymptotes which are odd multiples of 90 degrees, correct? So they become kind of a boundary. Within this boundary, we get the tangent function as shown here, and this really is very easy to draw and it can be replicated for the required domain. Perfect. That's the whole idea. So the tangent function is odd, so the interval from minus 90 to 90 degrees, or you can say from minus pi by 2 to plus pi by 2, will be considered as the principal cycle, right? So that is how we are going to do it. So always we'll try to sketch it within the domain from greater than minus pi by 2 and less than pi by 2. That is how we're going to do it, correct? So let's have some values for the tangent function. For degrees 0, 30, 45, 60 and 90, we know the values are 0, square root 3 over 3, 1 and square root 3. Now, for 90, we know it is a vertical asymptote, and so y approaches infinitely large value. That is from the left side, correct? Let me write this from 90 from the left side. Okay. Now, since it has odd symmetry, you can also find the values for the negative 0, negative 0, 0, negative 30, negative 45, negative 60, and negative 90. Now, approaching that negative 90 from the right side, correct? So, you could do that, which is this part, correct? So, those values will be negative of what we have written here, since it has odd symmetry, and therefore I didn't really mention those values. So basically, we will get these 3 points and the behavior, and that can be repeated because it has odd symmetry reflected about the origin to get the rest of the points. Well, if you're working in radians, in that case, for 0 radians it is 0, pi by 6, square root 3 over 3, pi by 4 it is 1, with pi by 3 it is square root 3, and for pi by 2 it is approaching infinitely large value. When we say odd symmetry, as I told you earlier, that means tan of minus x is minus of tan x. Correct. And the function is always increasing in its domain. That's kind of important to understand. Now, with that in mind, let us also see some key parameters which will help us to graph the function. So we'll begin with to understand how do we graph y equals to a tan kx plus q. So we'll consider vertical stretch and compression, horizontal stretch and compression, and vertical translation. So in this example, initially, we will not consider the phase shift. We are going to include the phase shift in the later half, but let's master all other transformations. So always when we talk about transformations, the parent function has to be y equals to tan x, correct? That becomes the base. So the points to consider are very simple. They're just these 3 points, correct? Which are at minus 45 degrees, we have minus 1 as the tan value. At 0, it is 0. And at 45 degrees, it is 1. So these 3 points are identified on the graph, and their image helps us to find the equation, or if we are graphing, in that case, setting those points as the image and connecting them gives us the graph. Vertical asymptotes, which are at plus and minus 90, forms the boundary for our principal value. And you know its period is 180 degrees, which is in between these plus and minus 90. And this function is always increasing with odd symmetry. Odd symmetry means it is symmetric about the origin. Correct. So if you have a function which is y equals to a tan kx plus q, in that case, the mapping of the points will be what? So x and y coordinate values will actually map to the x values will get multiplied by 1 over k or divided by k, and the y values gets multiplied by a and translated q units up if q is positive. If q is negative, that means it will come down by q units, right? So that is for our function y equals to a kx plus q as mentioned here. It really means that there is a vertical stretch by a factor of a, horizontal compression by a factor of k, 1 over k. Normally, we write this as 1 over k, right? And vertical translation by q units. Period for this particular function will be pi by k because the graph has been horizontally compressed by a factor of 1 over k. It is decreasing if a is less than 1. Normally it is increasing, right? So this graph is always increasing as we have mentioned here, right? Always increasing. If, however, the value of a is less than 0, means negative, in that case the graph will be decreasing, correct? Makes sense. Note, the tangent function increases from minus infinity to plus infinity. They do not have amplitude because there is no turning point kind of thing, right? We have used lowercase a, the stretch factor, to signify stretch or comparison factor, right? So what we're trying to say here is this lowercase a is being used on purpose. It's not an amplitude. So when you look into sinusoidal functions, sine, cosine and all, there we'll use capital A to signify that to be the amplitude for the graph, okay? Now with that base, let's begin with some examples. Example number 1. You can actually read the question, pause the video, answer, and then look into my suggestions. Example 1 is describe transformations of y equals to tan x to sketch the graph of the function y equals to minus 3 sine tan 2x minus 4, right? So that's the function which we are going to describe, y equals to minus 3 tan 2x minus 4. And once you've described that, then provide the mapping for the image points. Now let's look into this function. Now what do you get? Always start from left to right. That will give you a correct order in which you should be performing the transformations. Perfect. So the very first one, which is minus here, it means reflection on the x-axis. Then we have 3, and that means vertical stretch by a factor of 3. The 2 here, the k value, means a horizontal compression by a factor of half. And then minus 4 means vertical translation of 4 units down. So I hope that is absolutely clear. Perfect. Now based on this, any point, the pre-image point x and y, will now get transformed, and the image point will be what? Well, divide by value of k, and the value of a will be multiplied, in this case minus 3, right? And plus q. So in this case, let me write specifically, the formula will be, because the k is 2, so it has to be x divided by 2, okay, and minus 3 y minus 4. So that becomes the value. Since we have, let me rewrite this, that is better, minus 3 y minus 4, okay, that is better. So now let's look into the transformation of points. So we'll take xy values, and now we understand that the image point will be, x values will be half, and the y values will get multiplied by minus 3 and then take away minus 4. So as far as minus 45 degrees minus 1 is concerned, half of minus 45 is minus 22.5, and when you multiply negative 1 by negative 3, you get positive 3, and positive 3 minus 4 is negative 1, right? So that's how you get this point. When you're multiplying by 0, half is 0, and for 0, when you multiply by negative 3, it is still 0, but negative 4 will be there. So for 45 degrees, 22.5 is half of it, and y value of 1 multiplied by minus 3 gives you minus 3, and minus 4 is minus 7. So these become the 3 points transformed images of the given points. Now let's look into the vertical asymptotes. So on the graph of tan x, we have when x approaches minus 90 degrees, y approaches negative infinity. On the other hand, on the transfer function, the x value gets divided by 2. So when x approaches minus 90 divided by 2, it should be. So that is to say, when x approaches minus 45 degrees, in that case, y approaches positive infinities because of that minus 3, right? It is going to reflect it, correct? So what you notice here is that the period actually decreases. So in this particular case, let me mention here that the period will be what? Period will be 180 degrees divided by 2, which is 90 degrees. And therefore, the principal transform function will be between 45 degrees minus 45 degrees to positive 45 degrees. You get the idea, correct? And therefore, what is going to happen is that the vertical asymptotes, which were at minus 90 degrees and plus 90 degrees, will now be at 90 by half, plus and minus, correct? So when x approaches positive 45 degrees, in that case, y is going to approach negative infinity. So that is how the vertical asymptotes, behavior near vertical asymptotes will change for the given function. So I hope this concept is absolutely clear. Now, let's take up the next example, which is sketch the graph of y equals to 3 tan half x plus 1. So we'll map the points in the principal cycle, which is from minus 90 to plus 90, which is given in the table here. This is kind of similar exercise as we did earlier. And then we'll repeat the cycle to show the complete graph of tangent function. Now to begin with, let's try to analyze the function, which is y equals to 3 tan half x plus 1. And clearly, in this particular case, the period will now be what? Since it is half x, it is going to be stretched horizontally by a factor of 2. So the period will be 2 pi or 2 times 90, which is equals to 180 degrees, correct? So, 2 times 180, which is equals to 360 degrees. So now the period will be stretched to 360 degrees for the whole cycle. So which we are going to take from minus 180 to plus 180, right? So you see these vertical asymptotes, they are spaced between minus 180 to plus 180 for the graph of the given function, which is 3 tan half of x plus 1. Clear? Now let's also write down the transformations in this case. One transformation is vertical stretch by a factor of, and the other one is horizontal stretch by a factor of 2. Correct? So this horizontal stretch by a factor of 2 changes the period. That is what it is. So it becomes 360 degrees for us, correct? Now let's work in degrees for the time being as shown in the mapping diagram. Now let's look into the mapping diagram itself. The critical points which we are always going to take is these 3 points. Normally, I prefer to call them as A, B, and C, right? And these are the images A dash, B dash, and C dash. So the mapping will be that the x values will get multiplied by 3, right? So this will be 3 times 2x, and the x values will get multiplied by 2, that is the horizontal stretch by a factor of 2. The y values get multiplied by 3, and 1 is being added. So when you multiply minus 45 by 2, you get minus 90, and to minus 1, when you multiply by 3 and then add 1, you get minus 3 plus 1, which is minus 2. So that is how you can calculate the image points for A, B, and C. So we get the image points as minus 90 degrees minus 2, 0 degrees 1, 90 degrees 4. Now let's talk about the vertical asymptotes. The one at x equals as x approaches minus 90 degrees, the graph tangent x approaches minus infinity. In this particular case, when x approaches twice minus 90, which is minus 180, in that case it approaches minus infinity as being shown here, right? On the other side, also, when x approaches 180 degrees, in that case y approaches positive infinity. As you can clearly see that the domain, the period has doubled, right? It is now of 360 degrees. Perfect. So that is how we get that. Plotting these 3 points as shown here gives us the position. So for the principal part, we'll plot the points, right? Once you plot these points, then connect them as shown here, clearly indicating that there are vertical asymptotes at minus 180 as drawn here, correct? And the graph approaching minus infinity on the left side, positive infinity on the right side. Once you've done that, then repeat this pattern with a period of 180 times 2, which is 360 degrees, and you get the graph. You get the idea, correct? So that is how we should be sketching. So remember, we have a period in this case of 360 degrees, correct? So that is kind of important. Now let's move on and check example 3. We need to sketch the graph of y equals to minus 3 tan half x plus 1. So let's begin with the period itself. So in this case, the period will be what? It is getting multiplied by 2, right? So once you multiply that by 2, so it is normally 180. 180 times 2 will be 360 degrees. So we have a period of 360 degrees in this particular case. Now, deciding about the reflection, minus 3 tan half of x plus 1 is the example given to us. We earlier discussed its transformation. Now we are going to sketch it, correct? So in example 1, we discussed this particular a similar graph. Now we are going to sketch this particular graph, okay? So we'll map the points for the principal cycle, which is considered to be between minus 90 and plus 90, right? So the table here indicates the values for the points A, B, and C. And we'll get the image points A dash, B dash, and C dash. The mapping here is the x and y values will be mapped to the x value gets multiplied by 2, so 2x. The y values get multiplied by minus 3, and then you add 1, correct? So that is the mapping. So do your calculations. Once you do the calculations, the point minus 45 degrees minus 1 will be mapped to minus 90 degrees 4. 0, 0 will be 0, 1. 45, 1 will be 90 minus 2. The end behavior. See that minus flips it, correct? So instead of increasing, the function now is decreasing function, correct? Perfect. So when x is approaching minus 90, y is approaching minus infinity. But on the transform function, when x is approaching twice minus 90, which is minus 180 degrees, y is approaching the negative infinity is negative, which is positive infinity. Got it. So we are showing this with this particular arrow here, correct? When x approaches 90 degrees for the original parent function. So in transform case, it becomes x approaching 180 degrees. In that case, y is approaching the negative infinity as shown here. The 3 key points are A dash, B dash, and C dash. You see that. So connecting them with a curve as shown here and drawing the vertical asymptotes at minus 180 and plus 180 gives us the principal cycle. Now repeat this cycle to get the graph of tangent for the other parts of the domain. Clear? So that is how we're going to do it. Now let's take up example 4. Now in this particular case, we'll write the function of the form y equals to a tan kx plus q from the graph given. So we are given a graph this time. Perfect. We are given the tangent graph. It is increasing all the time. Leading coefficient is positive clearly. Correct. And we need to find the equation from the graph, right? That's the idea. So in this case, find equation of the given graph. Correct. So let's try to analyze the given graph. First thing which we should look into is the vertical asymptote, right? That is very clear. So when you look into the vertical asymptotes near the y-axis, parallel to that, of course, then what do you notice? You see that the vertical asymptotes are pi by 2 apart, right? So they are from minus pi by 4 to pi by 4, correct? So they are pi by 2 apart. So this distance between is is basically equal to this distance is equal to pi by 2, right? So that means the period is pi by 2 for the tangent function. And we can find the k value, which is pi by time period. So pi by 2 gives you the k value of 2, right? So the vertical asymptotes give you the k value. So remember this, vertical asymptotes will giving us that the k value is equal to 2 in this particular case. Now, let us analyze the point A, B, and C. So we normally the point B, which was supposed to be at the origin, we are going to check that point first. So when you check the position of the point B, it is now at 0, minus 1. Now this minus 1 indicates that the graph is translated vertically by 1 unit down. So the Q value is minus 1. You get the idea. So the point B, we should say B dash, which in this case is 0 minus 1, indicates that Q is minus 1 for the given function, which is A tan kx plus q. So we got the value of k, we got the value of q. Now it is question of vertical stretch. To find the value of A, you have to check the value of A prime. Now in this particular case, the y value of A prime is 2. Right? So what we notice here is that from B, it is 3 units away, not 1 unit, but 3 times away. You get the idea. So since the difference, that increment between the y values of A and that of B is 3, we know that the stretch factor A is 3 in this particular case. You get the idea. So from the points A dash, B dash, and just from A dash and B dash, we actually get all the 3 parameters required. And so that gives us the equation of the transfer function, which should be 3 tan 2x minus 1. Is that clear to you? That is how we are going to do it. Now here is the last question, which is kind of a test question for you. In the last example, we are going to understand how do we figure out the phase shift from the given graph. We'll write the equation in the form y equals to a tan k x minus p plus q. So let me write down the function here. We will write in the form of y equals to a tan k x minus p plus q. So to analyze the situation, it's a good idea to read the value for the vertical asymptotes, right? So we can start with the vertical asymptotes themselves. So the first vertical asymptote, which we see on this side, is what? The value here is x equals to minus 75. And on the right side, the vertical asymptote is x equals to 105. Correct? So once you know these two vertical asymptotes, right? In that case, you find the period. So a period will be the difference between the two. So which is 105 minus 75, right? And that gives you minus of minus 75. So it adds up, correct? So that gives you a value of 180 degree itself. So the period is 180. The value of k will be 180 divided by 180. So the value of k is 1. So we get the period from this. We know now the value of k, which is 1. Now we can find the phase shift also, since normally the graph will be from minus 90 to plus 90, and in this particular case it is from minus 75 to 105. Clearly we have a phase shift of 15 degrees, right? So the graph has shifted 15 degrees right, and that gives us the value for P as equal to 15, correct? P is 15 degrees. So we have the phase shift P as 15 degrees. You can also confirm this from the points A dash and B dash. The point B dash, which is given here, can be written as, if you can read it from the graph, it is 15 degrees, 0. Now instead of being at the origin, it has shifted 15 degrees to the right, and that gives you the value of P as 15. Now there is no vertical translation since the point is still the x-intercept, right? Now looking at the A value in this case is, now let's write down A as 60 degrees and 1. So the vertical stretch is also not there since it is still 1 unit away. So the value of A is equal to 1. So that gives you the function itself. You can now write the function as y equals to tan x minus 15 degrees. So the original function y equals to tan x has been translated 15 degrees to the right. So that is how we could do it. The domain of this function will be from minus 75 to 105 for one cycle, one principal cycle we can call this, right? You can always repeat this cycle to extend the graph in the entire domain. So I hope you understand the concept. Begin with the vertical asymptotes to get the equation that give you period. Then the points A, B, and C actually gives you translations. So that should really help you. The point A gives you the vertical stretch. Perfect. So that is how we'll summarize and close this lesson today. We'll also now take up a similar lesson on cotangent graph. So we'll add more information to this and see how to sketch a cotangent function and how do we find equation of that function's graph. So I hope you find it interesting and useful. In case you want to learn from me, you can always send an email to the address given. Also check our website for the new videos being uploaded. Thanks for your time and all the best.